Welcome. Today, we're diving into the qualifications of clean rooms, focusing on the recovery test. I'm Dr. S.K. Singh, and together we'll explore how these tests ensure clean rooms meet the highest standards for safety and efficiency. Let's get started. Let's talk about the recovery test principle. After we introduce particles into the clean room, the particle concentration rises. Then, the HVAC system kicks in, removing those contaminants. We measure the time it takes for the cleanroom to recover, to get back to its specified cleanliness level. This test shows us how well the HVAC, filtration, and airflow systems work together to clear contamination. It's a key way to prove the cleanroom's performance and support aseptic assurance. Recovery testing serves a clear purpose: to make sure our cleanrooms bounce back quickly and effectively after cleaning or disruption. We want to verify how well cleaning removes contaminants, evaluate how the HVAC system supports air quality, and assess how fast the environment recovers. It also confirms that the cleanroom maintains its classification and meets strict GMP standards. This testing applies across many critical areas, from sterile manufacturing and aseptic filling to semiconductor cleanrooms, operating theaters, and biosafety labs. Ultimately, faster recovery times mean better performance. When it comes to cleanrooms, regulators expect them to bounce back quickly after any contamination event. That means returning to their required cleanliness levels within a set timeframe. Typically, the industry aims for recovery times of 15 to 20 minutes or less. Various standards and guidelines back this up, from ISO and EU GMP to FDA and WHO, each outlining how to test and verify cleanroom performance. This slide highlights those key regulatory expectations and the benchmarks we use to measure success. Let's walk through the recovery test principles step by step. First, we establish a baseline by recording the initial particle count. Next, we introduce a particle challenge. This can be through aerosol generation, simulating personnel activity, or releasing powder. As a result, particle concentration peaks, exceeding the acceptable limit. From there, we continuously monitor the particle count until it drops back to an acceptable level. Finally, we calculate the recovery time, the duration it takes to return to the cleanroom's classification standard. When we think about recovery time, several factors come into play. First, air changes per hour. The more frequent the air cycles, the quicker the space clears out. Then, airflow patterns matter. Uniform flow helps sweep away particles efficiently. HEPA filter efficiency is key too. Higher efficiency means better contamination removal. Room size also affects recovery. Bigger rooms usually take longer. Equipment layout can create dead zones if airflow is blocked. Personnel movement stirs things up, increasing particles. And finally, pressure cascade. If pressure isn't balanced right, recovery slows down. When it comes to qualification equipment, there are a few key requirements we need to keep in mind. Instruments must be calibrated, sampling locations clearly defined, and HVAC systems stable throughout the process. For monitoring, we rely on real-time particle counting, trend recording, and graphical recovery analysis to get a full picture. The main tools include laser particle counters, aerosol and smoke generators, differential pressure gauges, and anemometers. Typically, we focus on particles around 0.5 and 5 microns, sizes that really matter for contamination control. Here, we see how the particle count dropped over time in the cleanroom. Starting at 120,000 particles, it steadily decreased until, at 15 minutes, it reached an acceptable level below the target limit of 3,520 particles per cubic meter. This means the cleanroom recovered successfully within the expected timeframe. The recovery time, 15 minutes, confirms the environment returned to safe conditions efficiently, meeting the cleanroom's strict standards. Let's walk through an example of calculating recovery efficiency. We start with an initial particle count of 100,000, and after the process, only 2,500 remain. Using the formula, we subtract the final count from the initial, divide by the initial count, then multiply by 100 to get a percentage. Here, that gives us a recovery efficiency of 97.5%, which means the contamination removal was excellent. Let's walk through the recovery test procedure step by step. First, we stabilize the HVAC system, making sure it's running under the right conditions. Next, we record a baseline particle count to know where we're starting from. Then, we introduce a controlled particle challenge, either with an aerosol or some activity. After that, we monitor how the particle count drops over time. We measure the recovery time, the moment the system meets the required standards. Finally, we document everything, creating a detailed report with trend graphs. Now, let's walk through the key stages of recovery test qualification. We start with design qualification, where we review the HVAC design, assess airflow recovery capabilities, and evaluate risks. Then comes installation qualification, which focuses on verifying instrument installation, HEPA filters, and calibration. Operational qualification follows, involving recovery test execution, particle monitoring, and alarm checks. Finally, performance qualification ensures dynamic operational recovery, trend analysis, and long-term monitoring. Each stage builds on the last, making sure the system performs reliably under real conditions. Now, let's look at the additional expectations we have for the system's performance. We're aiming for consistent recovery times, ideally between 15 and 20 minutes. Test results need to be repeatable, so we can trust what we see. HVAC operation must stay stable, with airflow and pressure holding steady, and no abnormal turbulence allowed. These acceptance criteria help us ensure the environment meets the strict standards we need for reliable, safe operation. When cleanroom recovery tests don't go as planned, we need to dig into corrective actions. Increasing air changes per hour helps speed up contamination removal. Replacing HEPA filters fixes leaks that can cause persistent high particle counts. Rebalancing airflow and repairing leakage paths tackle uneven recovery and instability. Finally, requalifying the cleanroom confirms everything's back on track. This slide breaks down common problems, their causes, and impacts, giving us a clear roadmap for troubleshooting typical recovery test failures. Let's look at a real example from a sterile filling area. Initially, the recovery test took 32 minutes, way beyond the acceptable limit. The Grade B area didn't pass qualification. Digging deeper, we found airflow velocity was too low, one HEPA filter was partially blocked, and air balancing was off. So we replaced the filter, corrected the air balancing, and adjusted the fan speed. The result? Recovery time dropped to 12 minutes, and the cleanroom was successfully requalified. This shows how precise adjustments can make a big difference. Recovery testing shows us how quickly a cleanroom can bounce back after contamination. It's a vital check proving controlled conditions are restored fast and reliably. To succeed, we need proper airflow design, efficient HEPA filters, a stable pressure cascade, and accurate particle monitoring. This testing ties directly to demonstrating HVAC performance, verifying contamination control, meeting regulatory standards, and ultimately assuring sterility. It's a critical step in keeping cleanrooms safe and compliant. Thanks for joining me today. If you want to dive deeper or have any questions, please don't hesitate to reach out. I'm here to help. And once again, thank you for your time and attention. It's been a pleasure sharing this with you.